The next stage in our exploration of non-dimensionalization is to consider how to non-dimensionalize a coupled system of partial differential equations. We're going to look at the Rayleigh Benard equations, which are often used for modeling convection as our archetypical coupled system of equations. The Rayleigh Benard equations have a number of terms. They've got three equations and three unknowns, one vector and two scalar. These are a continuity equation. The divergence of u is equal to 0. A temperature equation, d by dt of t plus u dot grad t is equal to a diffusion of temperature. The diffusion coefficient here is chi or he, the thermoelectric coefficient of diffusion right there. Our other equation in the system is the momentum equation. And what's new about the momentum equation now is that we have a coupling between momentum and the scalar t. We call t an active scalar because it is a scalar that can actually drive the flow. We've got u dot grad u is our typical pressure term. So this is our reduced pressure in the incompressible approximation pomega. And we've got our buoyancy, or excuse me, we've got our diffusion term, viscosity, nu del squared on u, and then we've got a buoyancy term. This is our new term linking temperature with pressure, temperature with motion. So this term comes in as minus alpha g vector. G here, this is equal to g vector is equal to minus g z hat. And alpha here is the expansion coefficient. This has units of 1 over temperature. And this basically says for a given amount of temperature change, how much does my fluid expand or contract in the Boussinesq approximation? G has units of length per time squared. U has units here of length per time squared, so alpha t is a unitless combination. All right, as we go into our non-dimensionalization, we're going to identify characteristic quantities to do our coordinate transformation. So we're going to have the dimensional temperature. This is equal to some characteristic temperature times a non-dimensional temperature, which we'll represent in green just for a notation here. Likewise, we're going to have some length scale x. This is equal to some dimensional length scale times a non-dimensional x. We're going to have a time scale t is equal to some dimensional tau and then some non-dimensional time t. We also have our variable pomega. That's going to be equal to some pomega naught. We're going to see that's going to be arbitrary, our characteristic pomega, and a non-dimensional pomega. And we have our velocity u, which is equal to some characteristic u times our non-dimensional u. Now, the characteristic u is a little special because in this case, u is actually given by an evolution equation. And that means that the scale of u is tightly linked with our decisions about our time scales and our length scales. And so for now, I'm going to just propose a lemma, which is that the u characteristic, this is given by our chosen length scale and our chosen time scale, tau. We'll see the implications for this as we work through this. All right, so let's start non-dimensionalizing our equations. Let's start from the top. Let's start from our divergence of u equals 0 equation. So this is our dimensional part. So we're going to have we're going to pull out our u characteristic and we're going to pull out our length scale here, and then we're going to have our non-dimensional div dot u is equal to 0. And we can see that equations of this form, where there's a simple set of terms and the right-hand side is equal to 0, these sorts of especially algebraic constraint equations, the dimensional form and the non-dimensional form are exactly the same. because our dimensional part here, this can be divided across to the other side, which is 0, and that doesn't change our system at all. So the non-dimensional continuity equation is just that div u equals 0. Okay, let's move on to the next equation. Let's go on to the temperature equation. So our temperature equation, writing that up in dimensional form, we've got d by dt of T plus u dot grad T is equal to chi del squared T. And now we're going to non-dimensionalize this. We're going to pull out our T characteristic and our tau times d by dt of T. We're going to have our u characteristic over L times T characteristic. Those are the dimensional bits of our u dot grad on T. And then we're going to have our dimensional diffusion coefficient, our dimensional length scale squared coming out of our Laplacian, and the characteristic temperature Tc times the Laplacian of T. As before, since all terms are proportional to T, the T characteristics fall out of the system. We now take our system with a 1 over tau in front of the d by dt, and we multiply by tau across all of our terms. So I'm going to collect some terms here for a non-dimensional system, d by dt of the temperature T plus u dot grad T, and we'll fix up our leading coefficients in just a moment. Is del squared T, those are our non-dimensional bits. And now our dimensional bits, we've got a uc tau over L, and we've got a chi tau over L squared. Okay, so here is our here's our non-dimensional T equation, where we've collected all of our timescale ratios in these two terms. We have a term here that's our advection to timescale relationship, and we've got a term here that's a diffusion to timescale relationship. We'll pick the actual timescale in just a moment. Before that, we're going to non-dimensionalize the momentum equation in the same kind of way. So for our momentum equation, writing things down, we've got d by dt of u plus u dot grad on u, and this is equal to minus grad on our reduced pressure pomega minus alpha, well, let's make this plus alpha g scalar T in the z hat direction plus a nu del squared u. So here's our fully dimensional form. Again, this has units of length per time squared, so this has units of 1 over temp. I've got my capital T confusing with the T here, but this has units that combine with the temperature, leaving a length per time squared, so that we agree with the units on our dimensional acceleration term, d by dt of u. All right, let's now non-dimensionalize this. So as we collect our terms out front, I'm going to leave u characteristics in here for now. I'm not going to use our lemma until a few moments from now. We've got d by dt non-dimensional of u. We've got our u dot grad on u, and we've got the term u characteristic squared over L as our dimensional component. This is equal to, we'll keep this term for now, minus pomega naught over L grad of non-dimensional pomega. We've got our alpha g t characteristic non-dimensional T in the z hat direction, the vertical direction, and then we've got our diffusion term plus nu over L squared u characteristic and then non-dimensional Laplacian on u. The thing that's different in this equation from other equations we've seen before is that we have a t term and then a whole bunch of u terms. So we're actually mixing different terms. We also have a pomega term, but that ends up being simple because we're in a constrained set of equations with the divergence of u equals 0. Pomega ends up being the Lagrange multiplier and freely rescales. But we still have this t term here, which is of a different kind of units than our u term. So that we're going to end up with a ratio of our u characteristic to t characteristic rather than having u characteristic cancel out of the equation throughout, as we're used to, for example, in the t equation where t characteristic canceled everywhere. So let's take our leading term here. Let's multiply the whole system by tau over uc to eliminate that term, and let's write down the resulting system. All right, we've got d by dt of u plus u dot grad on u. We've got a minus and a grad pomega. We've got our t in the z hat direction, and we've got our Laplacian of u. And let's now go fill in our dimensionless, non-dimensional numbers here. So here we have uc tau over L. Here we have a pomega naught. We have a tau, and we have a L times uc, and then here we have an alpha, a g, a t characteristic, a tau divided by u characteristic, and here we have a nu, a tau, and an L squared. All right, so there's our system of equations. We've got our momentum equation right here. We have our temperature equation that we had derived a few moments ago right here, and we have this coupled system of equations. Now, the thing about our coupled system of equations is that we need to choose a consistent time scale, and we need to choose a consistent length scale for all the equations because we have two partial derivatives with respect to time, and if the one on the temperature equation and the one on momentum equation are operating on fundamentally different physical times, then we have an unphysical system. So we can make multiple choices. There's several good and valid choices. Here, guided by simplifying the temperature equation, we're going to choose that our time is the thermal diffusion time. So we're going to choose that L squared over chi is our time scale. We're also going to choose that the u characteristic is L over tau. That was our lemma from earlier. And we can see that under this particular choice, if uc is L over tau, if this is an L over tau, then this term is going to become 1. And based on our time scale choice, this term is going to become 1. So let's go start writing down our system of equations for our combined non-dimensional system. And we'll leave our momentum equation, the one that is going to take the most care in view, as we write down the equations we already know. So we know that the divergence of u, that equation was already non-dimensional, or dimensionalizes in a trivial fashion. We then have that d by dt of t plus u dot grad t non-dimensional is equal to del squared t. There's our non-dimensional temperature equation, and now we need to apply the same logic to our momentum equation. And I'm gonna recall that we've chosen here that t is L squared over chi, and that u characteristic is L over tau. So we're gonna apply these up in the momentum equation. So for our momentum equation, our first term is already fully cleaned up. Our second term, that's going to go to 1 because of uc being L over tau. This is going to be equal to 1. So let's write that down now. U dot grad u. We're going to have our third term here. So this is omega naught, and I'm going to actually insert. I'm going to invert my my UC here. We could also say that tau is equal to L over UC, and I'm going to substitute that in for tau in this spot. So this actually becomes omega naught over UC squared times grad omega. And we'll go down to the next line for our next set of terms as we get into the buoyancy term. So our buoyancy term here, we are going to have an alpha, a t characteristic, a g, and I'm going to substitute in for my UC. So we're going to have a tau squared. I'm going to do this sort of step by step. So this is tau squared over length times our non-dimensional temperature, and we'll return to this in just a moment to finish cleaning this term up. But let's get our viscous term up. We've got a nu over L squared times tau, which is L squared over chi times the Laplacian of u. I'm writing these out with some care because we have a couple of new non-dimensional numbers in this system. The first of these non-dimensional numbers shows up in front of the omega term. We have omega naught over u characteristic squared. And omega is p naught over rho naught over u characteristic squared. And if we were in an ideal gas, that would be something like our T naught over U characteristic squared for an ideal gas. And this is actually our sound speed squared. So this whole term here is equal to the Mach number squared to the minus 1 over the Mach number squared, where the Mach number is defined as the characteristic velocity over the speed of sound. So our leading term in front of our omega looks something like Mach number to the minus 2. All right, what about our viscous term? Let's hop to that, and then we'll come back to our buoyancy term. Our viscous term here, our length scaled squareds, those cancel away, and this leaves this term, nu over thermal diffusion chi, and this is actually our Prandtl number. Prandtl. Mach. So we've got a Prandtl number in front of our viscous diffusion coefficient. Let's look at our last term here, the alpha TCG tau squared over L. Let's write this down. So this is our expansion coefficient times our characteristic temperature times G times tau over L. And let's now insert our definition, or excuse me, tau squared over L. Let's insert our definition of tau. This is TCG L to the 4th power over L and chi squared. One of the L's goes away here. This L cancels out at the bottom. And in total, we have this term that's alpha TCG L cubed over chi squared. This term is related to a well-known non-dimensional number in fluid dynamics called the Rayleigh number. So I'm going to introduce the Rayleigh number right now. And the Rayleigh number is alpha TCG L cubed over the mixture chi nu. So that is equal to our number up here times a Prandtl number. Let's call our number up here just number. So that's equal to our number up here, divided by a Prandtl number. So this is our Rayleigh number. So that means that our number is itself a Rayleigh number times a Prandtl number. Okay, that's quite a mouthful. So let's come back up to our momentum equation here. let's relabel our various terms. So this term here, this is Rayleigh times Prandtl. This term here, this is a Prandtl number. And this term that we don't usually see it in the Boussinesq approximation, this is technically a Mach number to the -2 that ends up getting freely absorbed into the omega. Let's come down and write our coupled set of nonlinear partial differential equations under a thermal diffusion timescale, including our Rayleigh number that's here. So our coupled system is that the divergence of u is equal to 0. It's that the partial derivative of t plus u dot grad on t is equal to del squared on t. And it's that the momentum equation is d by dt of u plus u dot grad u plus, I'm going to move the pomega over to the left-hand side, grad pomega is equal to a let's do our dimensionless numbers in blue, is equal to a Rayleigh number times a Prandtl number times a temperature fluctuation moving in the z hat direction, and then plus a Prandtl number operating on the Laplacian of our velocity u. Here's the full set of equations for Rayleigh Benard convection under the Boussinesq approximation, using that the timescale tau is given by the thermal diffusion timescale. Tau is equal to L squared over chi. As we look at the system of equations, we can see some clues to the non-dimensionalization that was done. We can see those clues in the fact that the non-dimensional numbers remaining are in the momentum equation, they're on the buoyancy term, and they are on the viscous diffusion term. But when we look at the temperature equation, the diffusion term and the advection term do not have non-dimensional numbers. That can clue us in examining visually a set of equations that the system's been non-dimensionalized based on the diffusion time here of the temperature system. This system has some rich dynamics. We'll be learning about those later on, but it's our first experience with sort of a fully coupled system of equations with a non-trivial active scalar driving the momentum equation, and with the momentum equation then reacting back on that active scalar. If we had some boundary conditions here on t and on u, we'd be ready to go forward and get solutions for this. Depending on those choices, your system can either be unstable to convection or it can present internal gravity waves under the Boussinesq approximation.